verify that minus 1 plus root 2i is the root of the equation. So we just have to replace the z with minus 1 plus root 2i. So that means we're gonna need z to the power of 4, z to the power of 2, and z. So this is the z squared is, we square this, so we get minus 1 times minus 1 and so on. So 1 minus 2 root 2i plus 2i squared. I squared is minus 1, so this is actually minus 2. 1 minus 2 is minus 1. For the z to the power of 4, we square z squared here. So we square this one in blue here. So after we square this, we get 1 plus 4 root 2i plus 8i squared. I squared is minus 1, so this is actually minus 8. 1 minus 8 is minus 7. So we have everything, we plug in. This is the z to the power of 4, z to the power of 2, and z to the power of 1. Simplify everything. Times 3 times 3. And times 2, and we simplify for the real part, minus 7 minus 3 minus 2 plus 12, that is 0. And for the imaginary part, 4 root 2 minus 6 root 2 plus 2 root 2, that is also 0. So we have proven that minus 1 plus root 2i is a root. Find the other roots. Since we already know that minus 1 plus 2 root I is a root, that means the conjugate minus 1 minus root 2i is also a root. And since this is a root, then z minus this is a factor. So z minus the first root, z minus the second root, they are all factors of the equation. So we multiply the two linear complex factors to get a quadratic real factor. So when we multiply z minus this, just open up the brackets, minus minus we get plus, minus plus we get minus, open up the brackets, plus plus, and this is actually z plus 1 minus 2 root root 2i plus root 2i. This is actually the difference of two squares, a minus b, a plus b. So we have a squared minus b squared. So this is a squared, which is z squared plus 2z plus 1, and the b squared is 2i squared. I squared is minus 1, so this is actually plus 2. 1 plus 2 is 3. Okay, so this is the real quadratic factor of the complex function. Okay, now that we know the quadratic, we can do polynomial long division. So this is the original complex expression here, and we divide this by the quadratic factor. So we do z squared, because z squared times z squared is z to the fourth, z squared times 2z is 2z cubed, z squared times 3z squared, and then we subtract. When we subtract, we should cancel out the first term. 0 minus 2 is minus 2, 3 minus 3 is 0, and we drop the next term. And we have to multiply by minus 2z. Minus 2z times z squared is minus 2z cubed times 2z minus 4z cubed, z squared, and times again minus 6z, subtract, cancel out. 0 minus minus 4, that's positive 4, and 2 minus minus 6, that's 8, and drop the next term. So now we have plus 4 here, so plus 4 times z squared, we get 4z squared, plus 4 times 2z, 8z, plus 4 times plus 3 plus 12. So yeah, we subtract again, cancel out everything actually, so we have 0 only here because it's a factor, so the remainder is supposed to be 0. So this is the other quadratic real factor of the complex. Okay, so since we already know that this complex expression on the left here can be factorized into the two quadratics, and actually from this quadratic we get the first two roots. Now we need to find the other two roots from the other quadratic quadratic factor. So we use the quadratic formula. The z is x, the a, b, c are 1 minus 2, 4, plug into the calculator, and You see here, this is positive 2, this is 4, and this is minus 16, so we get 4 minus 16 is minus 12. So the square root of minus 12 is root 12 times root minus 1. Root minus 1 is I, and root 12 is 2 root 3. So divide by 2, we get 1 plus minus 2 root 3i, which means we have all 4 roots now. 1 plus minus 2 root 2i and 1 plus minus root 3i. Alright, that's the final answer. I'll see you again next time.